Hello dear students, welcome to a series of lectures in the course Limit State Design of Steel Structures. In this very first lecture, we will be discussing the advantages of structural steel and the specifications for various structural steel sections that are commonly used in practice. First of all, let me give you the list of recommended books and the codes of practice that you will need to follow in this course. So here is a list of reference books. Limit State Design of Steel Structures by S.K. Dugal, Steel Structures Design and Practice by N. Subramanian, Limit State Design of Steel Structures by Ramchandra, Fundamentals of Structural Steel Design by M.L. Gambhir, Structural Steel Design by Jack C. McCormack, Code of Practice for General Construction in Steel, that is IS 800-2007, Handbook for Structural Engineers SP6, Steel Table, Code of Practice for Design Loads IS 875-1987 and IS 2062-2011. So far as steel is concerned, structural steel as a building material has been extensively used in a variety of civil engineering structures. Some of the examples of civil engineering structures in steel are high-rise building skeletons, industrial buildings, transmission towers, railway bridges, overhead water tanks, steel chimneys, sports stadiums, and guide masts. As you can see, some of the steel structures are depicted in the picture. That is, we have a primary building, we have a braced building, we have a transmission tower, and we have an overhead water tank. All these structures are made up of structural steel elements. Most of the steel structures belong to the category of braced and rigid frame construction. They essentially consist of regularly spaced columns joined by beams or girders. Secondary beams span between the main beams and provide support to the concrete floor or roof sheeting. In the case of braced frames, the beams and columns are designed to resist vertical loads only. The connections are designed as pinned. So braced frames with pinned connections and vertical bracing systems offer a very cost-effective structural solution and are the most commonly used structural systems in buildings. Bracings are mainly provided to resist lateral loads due to wind and due to earthquakes and to provide stability to the structure. In braced construction, beams and columns are designed for vertical loads only, assuming the bracing system carries all the lateral loads. Whereas in rigid frame construction, the frame structure is designed so that the connections between the structural members are moment resisting. That is, they are capable of transferring the moment in addition to the shear forces. In summary, in braced frames, columns are designed to resist mainly compressive forces, while as columns in rigid frames are designed to resist bending in addition to compression. Structural steel is the most versatile building material available to structural engineers. Its unique properties make it a best choice amongst other building materials. The advantages of steel as a structural material are high strength to weight ratio. Structural steel has high strength per unit weight. Therefore, a steel member of a small section which has little self weight is able to resist heavy loads. The high strength of the steel results in smaller sections to be used and fewer columns in buildings as a result. The high strength to weight ratio is the most important property for the construction of long span bridges, tall buildings, and for buildings on soils with relatively low bearing capacities. Another important property of steel is uniformity, that is, invariability of properties. Greater control is exercised in the manufacture of steel. So, both the properties of steel and uniformity of structural shapes can be very well assured. Therefore, the designer has ample surety about the uniformity of the strength. Another very important property of steel is ductility. Steel, being a ductile material, does not fail suddenly but gives visible evidence of impending failure by undergoing large inelastic deformations before failure. Also, the ductile nature of structural steel enables it to yield locally at the points of high stress concentrations. Ductility is the most indispensable requirement in highly seismic regions. Therefore, steel is the better choice in comparison to reinforced cement concrete structures in regions of high seismicity. Another property of steel is weldability. Different structural elements of steel can be joined by welding, that is, it is weldable. Another property is high toughness. Toughness actually denotes the capacity of the material to resist fracture under impact loading. Both the strength and the ductility, they contribute to toughness. So, structural steel is a highly tough material and is capable of absorbing large amount of energy. Steel is also recyclable material. It can be recycled again and again. Additions and alterations can be easily made to the steel structures, whereas it is very cumbersome to do additions and alterations in case of RCC structures. Steel is also gas tight and watertight, that is impermeable to gas and water. It is easy to inspect and easy to maintain. It has longer service life if properly protected, and it is a faster rate of construction, whereas RCC requires installing shutterings, reinforcing bars, casting of concrete, which further requires ample time to fully develop the strength. But there are some disadvantages associated with steel as well. So these are high cost of construction. Steel structures have relatively higher cost of construction in comparison to RCC structures. Fabrication cost is very high in steel structures. In fact, materials account for 1/3 or less of the total cost of a typical steel structure, whereas labor costs can account for 60% or more. Another disadvantage of steel is high maintenance cost. Exposure to water and air has a devastating effect on the steel structures because of corrosion. This requires painting of steel structures on periodic basis, resulting in high maintenance cost. It has poor fireproofing. In case of fire, the rise in temperature results in drastic reduction in the strength of steel. Steel at 538 degrees Celsius has about 65% of the strength at normal temperature, and at 871 degrees Celsius it is about 15% only. Such a drastic reduction in strength results in collapse of a steel structure. Another disadvantage that is associated with steel is its susceptibility to buckling. As the length and the slenderness of a compression member is increased, its danger of buckling increase. For most structures, the use of steel columns is very economical because of their high strength to weight ratios. Occasionally, however, some additional steel is needed to stiffen them so they will not buckle. This tends to reduce their economy. Another property that is associated with steel and that is very fatal to the structure of steel is fatigue. It is an undesirable property of steel, and its strength may be reduced if it is subject to a large number of stress reversals or even to a large number of variations of tensile stress. Fatigue problems occur only when tension is involved in a steel structure. The present practice is to reduce the estimations of strength of such members if it is anticipated that they will have more than a prescribed number of cycles of stress variations throughout their life. We have brittle fracture under certain conditions. Under certain conditions, steel may lose its ductility and brittle fracture may occur at places of high stress concentration. Fatigue type loadings and very low temperatures aggravate the situation. Further, triaxial stress conditions can also lead to brittle failure of a steel structure. The majority of structural steel that is used as building material is hot rolled structural steel. The process of hot rolling involves rolling steel at a temperature above the recrystallization temperature of steel, which takes place at over 927 degrees Celsius. Steel that is above the recrystallization temperature can be shaped and formed much more easily than colder steel without any loss in ductility. In this process, hot steel continuously passes through a series of rollers that squeeze the material into the desired cross-sectional shape. The steel sections so produced are called rolled steel sections. Actually, they are hot rolled steel sections. So, structural steel is available in a variety of shapes and sizes. Mostly, the cross-sectional shapes are designated by a letter that indicates the shape series, followed by the depth of the member and the weight per meter length. The steel sections that we use in practice are rolled steel I sections or beam sections is also called universal beam section. We have rolled steel channel sections, rolled steel T sections, rolled steel angle sections, rolled steel T bars, rolled steel bars, rolled steel tubes, rolled steel flats, rolled steel sheets and strips, and rolled steel plates. These shapes are actually the cross-sectional shapes of the structural steel elements. Now, rolled steel I sections or beam sections have further been classified in Indian Standard Junior Beam, that is ISJB or JB, Indian Standard Light Beam, that is ISLB or LB, Indian Standard Medium Weight Beam, ISMB or MB, Indian Standard Wide Flange Beam, ISWB or WB, Indian Standard Heavyweight Beam, Indian Standard Column Sections. You can see the nomenclature for these beams. So, rolled steel I section has a shape as shown in figure. It resembles the letter I. That is, a cross section of this steel section resembles the letter I. This is the top portion and the lowermost portion, these are called flanges, and the vertical element in this eye section is called the web. We have slopes on the inside face of the flanges as shown in the figure. That is, it is not a horizontal member, it has a sloped face at the junction as well as at the edge. The slope on the inside face of the flange is approximately 16.66%. So this is the width of the section, that is, the width of this eye section is B, and this is called depth of the eye section from top to bottom. And this is the thickness of the web. But in order to determine the thickness of the flange, you will need to determine it at a particular point because it is sloped. So it has to be mentioned where will be the thickness measured. So thickness is generally measured at B minus TW, where TW is thickness of the web, divided by 4. So at this location, the thickness is mentioned. This is the longitudinal section of the eye beam. So the rolled steel beams are designed by the series to which they belong, followed by the depth in mm of the section and weight in kilonewton per meter, length of the beam. For example, MB225 at the rate of 0.312 kilonewton meter. It represents a beam section of medium weight and of depth equal to 225 mm. Similarly, OS-MB 400 means a beam section of medium weight and depth equal to 400 mm. Now we have rolled steel channel sections. These are the actually shapes of structural steel sections that are generally used in practice. That is, eye sections, rolled sections, etc. So rolled steel channel sections are further divided into 4 categories. That is, Indian Standard Junior Channel (ISJC), Indian Standard Light Channel (ISLC), Indian Standard Medium Weight Channel (ISMC or MC), Indian Standard Parallel Flange Channel ISMCP or MCP. So figure denotes the cross section of a channel section. This flange is a sloped flange. This portion is called the width of the flange. This is the web, and TW is thickness of the web, and D is the total depth of the section. And the thickness of the channel section is measured at a distance of B minus TW by 2. So at this point, we measure the thickness of the section, that is B minus TW, where TW is the thickness of the web, and divided by 2. The junction of the web and the flange is called fillet, as you can see in the figure. This is the 3-dimensional longitudinal section of channel. For example, ISMC 400 at the rate of 0.494 kilonewton per meter. It implies depth of the section is 400 mm and weight per meter length of the channel is 0.494 kilonewton. Now we have rolled steel T sections. It is further divided into 5 categories, that is, Indian Standard Normal T bars ISNT or simply NT, Indian Standard Deep T bars ISDT, Indian Standard Light T bars ISLT, Indian Standard Medium T bars ISMT, Indian Standard Heavy T bars ISHT. So these are the available shapes of the steel T sections that can be used in structural applications. The T section is shown in figure. It resembles the letter T. So this is the B, that is width of the section, and this is total D, this is depth of the section. And this is the flange, this is the web. For example, we have an T section of ISNT 80 at the rate of 0.960 kN per meter. It implies normal T section, that is ISNT normal T section of depth 80 mm, where D is the depth, it denotes the depth of the section, and of weight 0.96 kN per meter length. Now we have rolled steel angle sections. In this case, we have two angle sections available, that is Indian Standard Equal Angles ISA, and we have Indian Standard Unequal Angles, it's also denoted by ISA. An angle section is designated by its leg length and thickness. So this is an angle section, this is the cross section of a structural element whose shape resembles L, the letter L, or it is similar to an angle. So this is the length of the section, this is also the length of the section. It is an equal angle section. L is length of the leg, this is L is also length of the leg, so we say it is an equal angle section. So we have this called R2, that is toe radius, and this R1 is called root radius. So we have actually curved surfaces on the top as well as on the flat side. So we have two different radii, this is R1 and R2. It's a curved portion here and here. We have another Indian Standard Unequal Angle, that is in this angle we have different leg lengths. We have L1 and L2, that is L1 is not equal to L2, but whereas in case of equal angles L and L are equal, that is both the legs are equal, whereas in case of unequal angles we have different leg lengths. An angle section is designated by its leg lengths and thickness. For example, ISA 40 into 25 into 6 mm, it means the section is an unequal angle, that is one leg is 40 mm, another leg is 25 mm, and the thickness of the legs is 6 mm. Then we have rolled steel tubes or hollow sections. These are available in square hollow section as well as circular hollow section. Steel tubes are designated by their outside diameter or side end self weight. The rolled steel tubes are used as compression members and tension members in tubular trusses. The rolled steel tubes are efficient structural sections to be used as compression members. The steel tube sections of circular shape have equal radii of gyration in all directions. So they are a better choice to be used as compression members or as tension members. While designing a steel structure, if the design force for a particular structural element is large enough so that no available standard structural section meets the design requirement, then a compound section or a built-up section will be needed. That is, if the available sections will not be able to fulfill the design requirement, then we will have to make a compound section, or we will have to make a built-up section. So compound section, that is I section with cover plates, we can make a compound section. We can add cover plates on two flanges, so we can increase this section models are moment of inertia, so the load carrying capacity may be increased. Similarly, we can fabricate a section from different structural steel elements. For example, we can use different steel plates and join them by welding, as shown in this figure, and which resembles a letter I, and we say it is a welded girder or a welded I section. Then we have bull-tap sections. Bull-tap shapes can be created by attaching two or more standard rolled shapes to each other. The most widely used combinations are double angles or double channels placed back to back and connected at intervals along the length. As you can see, these are two angles and these have been connected back to back, and these are two double channel sections, that is two channels have been connected back to back along the length. So this is called a built-up section. We can make a built-up section in some another way, as we can have different plates. We can have flange plate, we can have web flange, and we can connect them, and we can further increase the moment of inertia or section modulus by attaching angle sections at the locations of flates along the length of this girder. So this is called plate girder. We have also double web box girder, that is we can fabricate a box girder which resembles the shape of a box. It is a hollow portion in between. So we have used web plates and flange plates, and we have connected them with angle sections. So we have actually distributed the mass and increased its moment of inertia as well as section modulus. So plate girders are used for heavy loads in buildings and bridges, and double web box girders are specially used for heavy flexural members subjected to torsion as well. Next we have rolled steel bars. In this category we have Indian standard round bars, that is ISRO, Indian standard square bars, that is ISSQ. As shown in figure, this is the round bar section, this is the square bar section of steel. Rolled steel bars are designated by diameter or side width. For example, ISRO 10 mm means a round bar of 10 mm dia, and ISSQ 10 means a square bar of 10 mm side. Rolled steel bars are usually used as ties and lateral bracings. Next we have rolled steel sheets and strips. In this category we have Indian standard steel sheet section, that is ISSH or simply SH. We have Indian standard strip section, that is ISST or simply ST. Steel sheets are designated by length, width and thickness. For example, ISSH 2000 mm multiplied by 600 mm multiplied by 4 mm. It means the sheet is 2000 mm long, 600 mm wide and 4 mm thick. Similarly, steel strips are designated by width and thickness. For example, ISST 200 by 2 means the steel strip is 200 mm wide and 2 mm thick. Then we have rolled steel plates. Steel plates are designated by length, width and thickness of the section. For example, ISPL 2000 by 1000 by 8 means the plate is 2000 mm long, 1000 mm wide and 8 mm thick. The rolled plates are used in the web and flanges of plate girders and plate beams and cord members and web members of truss bridge girders. The rolled steel plates are also used in special plate structures, for example, shells, rectangular and circular steel tanks, and steel chimneys. Then we have rolled steel plates. Steel plates are designated by width and thickness of the section. That is, it is a steel section whose width and thickness designated. For example, 30 ISF 10 means that the plate is 30 mm wide and 10 mm thick. As you can see, this is the picture showing a steel strip with width and thickness. So this is all in today's lecture. Thank you.